Hi, my name is hussnain Raza, and today I'm doing my presentation for operating system, and I will walking through you by my implementation for worksheet 1 and worksheet 2. So let's begin at looking my GitHub repository where all my project file and documents are stored. So as you can see, both repositories contain the complete source code. Now I will log into a UVCSCT cloud environment to demonstrate execution of my code. I am now successfully logged into the cloud terminal. Let's start with the worksheet 1 and echo for assembler. I'm going to navigate to the directory and the list the file. So as you can see from the directory structure, we have our source file and make file ready. The main goal here was to implement basic assembly program and link with the C driver. So let's look at task 1. I created an assembly program to add integer and return the result to a C program. This taught me how C and assembly communicate using the EAX register and how to preserve register states using the pusha and popa commands. I also did the extension task 1.2 to use variable from the data section instead of hard code values. Let me run both of these now. Okay, so the outputs are correct. Now moving to task 2, which involve loops and conditionals. I wrote a program to print a welcome loop based on user input, ensuring the number is between 50 and 100. This required using comparison and jump instruction in assembly. I'll run the task 2 now. So for the task 2 extension, I work with arrays to calculate the sum of numbers within a specific user provided range. Assessing array elements require calculating memory offsets for 32-bit integers. Let me demonstrate the range sum output. So finally, to automate all to this, I created a makefile in task 3. Instead of copying long complication commands, the makefile compiles the C file with GCC and the assembly file with the NSM. And I will run make clean and make to show the build process. So everything complies perfectly. Now let's transition to the second part of the assessment, worksheet 2, which focus on interrupts and keyboard input. I am navigating the worksheet 2 directory now. So looking at the structure, I separated the kernel logic into the source folder and the hardware drivers into the driver folder to maintain modularity. So for this worksheet, I first set up a standard data type. Basic are using NB and outB assembly function. Then I wrote a driver for programmable interrupt controller or PIC to remap hardware signals so they do not conflict with the CPU expression. After that, I configured the interrupt distributor table and set up an interrupt service routine for the keyboard. The code was the PS2 keyboard driver, which reads scan codes from port 0x60 and convert into ASCII tractor uh, using a switch case logic. I also update the main kernel entry point to include some math logic to verify C linking and enhance the frame buffer driver for custom text colors. And let me build the OS image now. So the ISO is successfully built since the CSCT server runs QEMU in hitless mode. Hitless mode, I can show a graphical window. Instead, I will run the OS and verify the execution by inspecting the video memory at address. This one using the QEMU monitor. Let me run this now. So as you can see in the memory dump on the screen, all requirements are met. The math logic shows the correct sum and the products. The frame buffer driver API shows the correct text color in memory. And most importantly, you can see the type below prompt, which confirm that the hardware interrupts are enabled and the OS is activated for keyboard input. So this proved that the minimal kernel, the interrupts, and the keyboard driver are all integer integrated and functioning correctly as per the assignment brief. This concludes my presentation for OS module. All the related code is already submitted in GitHub repositories. Thank you so much for your time and for your reviewing my work, and have a lovely day.